Hey guys, Chill here. Welcome back to Hardware 3D. Today, our video, we've got two main goals. Goal number one is to implement dynamic lighting. Goal number two is to just get a little introduction into the debugging tools that Visual Studio ships with for graphics. Allow us to debug our shaders and our graphics pipeline. So, first of all, dynamic lighting. Specifically, what kind of dynamic lighting are we looking at? Well, we're going to be doing per pixel lighting with a point light, and we're going to also be adding specular highlighting. So basically, it's going to be Phong shading. Now, I've already covered the theory behind this kind of per pixel lighting and specular highlighting in 3D fundamentals. So if you don't already understand that stuff, you really have to go and watch the video in 3D fundamentals. There's at least 3 videos that cover the kinds of diffuse lighting and specular lighting and just the idea of shaders and dynamic lighting in general. And if you don't know that stuff, you're going to have a hard time following this video. You're not going to really know how the math works. So let's take a look at the commits. There's a lot of them. Now, the first one, I just basically introduce the lighting into the system. Minimal stuff that we'll be improving on. And you can see here a bunch of stuff that's been added, a bunch of stuff that's been changed. Obviously, you're going to need a new pixel shader if you're doing per pixel lighting. And that pixel shader is going to need to take in normals. So that means that the vertex shader, we're going to also need a new vertex shader because our previous ones weren't dealing with normals. So let's look at the pixel shader, shall we? And if we look at it, the first thing you're going to notice, you might notice, is, hey, there is more syntax highlighting here. And that is because I've installed a very nice extension that I recommend you guys also install. Here it is. Here's the URL. It's called HLSL Tools for Visual Studio. And it adds better syntax highlighting. It adds formatting. And most importantly, it adds statement completion. That kind of IntelliSense that is going to make your life a lot easier when you're just learning HLSL. But yeah, we've got a new pixel shader here. It shouldn't be that complicated if you understand the theory. We've got a constant buffer that allow us to change the light position every frame. The other parameters for light, for the current moment, we're keeping them static. They don't change throughout the runtime of the program. But later on, I'm going to also make these dynamic through a constant buffer. Now, your pixel shader here is going to take in 2 parameters, the world position of the pixel and the normal of that pixel. And you calculate some vectors here, you calculate your attenuation, and then your diffuse, which is based on your dot product. This you should all know. And then you calculate your final color. So this stuff, not a big deal. Now, since this is our first HLSL shader that's doing something that is non-trivial, let's take a quick look at some of the new stuff that we're seeing here. One of the first things I want you to notice is the multiplication here. It's got some differences from what we've been doing in 3D fundamentals that you got to be aware of. So in 3D fundamentals, we overloaded this so that vector times vector multiplication would be a dot product. But in HLSL, that's not how it works. So you call the dot function or intrinsic function on 2 vectors to get the dot product. In fact, multiplication between 2 vectors with the operator gives you the Hadamard product, which means member by member multiplication. You'll see that a little later on when we multiply this down here times the material color. Other than that, things should be as you would expect. A scalar times a scalar is a scalar. Vector times a scalar is a vector. Vector plus a vector is a vector. Other than that, you're going to see we have a bunch of these different keywords here. They're highlighted in different color. That's because they are intrinsic functions to HLSL. And they're pretty easy to understand. Dot product is, like I said, very simple. You take the dot product to 2 vectors, returns a scalar. Maximum does, the same idea as std max, and there's also min. Length gives you the length of a vector. Saturate will saturate some value, vector or scalar, to 1. And I'm not going to explain all these functions as they come up. There are not a lot of them. Here's the whole list of all the functions in HLSL. You can check this page out. You just search Google for HLSL intrinsic functions and you'll get this page. And it's a good reference for all the functions here. So if we look up, for example, saturate, we can see it's available from HLSL version 1, clamps X to the range of 0 and 1. And if you click on it, you get the details. You see it works on any scalar, vector, or matrix of floats. So yeah, make sure you check out the Microsoft page on intrinsics and make sure you reference it while you're watching these videos in the future. The other new thing here is I create some global constants, and I can do that using static const. This stuff, not a big deal. Vertex shader. What do we got here? Again, we take in the position. We take in now also a normal, and we calculate the world position of the pixel, which is just multiplying it by the model transform. So in our C buff here, we're taking in two matrices, one for the model transform and one for the concatenated model view projection. So for the world position, we only want to multiply it by the model transform. And for the normal, we also want to multiply it by the model transform, but we want to cast that to a 3x3. We don't want that fourth coordinate because that will introduce the translation, but you don't want to translate your normals. You only want to rotate them. And then this is just what you were doing before, right? So again, shader shouldn't be too complicated, especially if you have followed along in 3D fundamentals. What else has changed? Well, because we've added normals now, we've got to add normals to our models. So to our cube, little library here for generating geometry, I have one that's generating independent faces for the cubes so that every face can get its own normal. And you might be saying, I don't see the normals here, Chili. Where are the normals? Well, for that, I've actually added a function to index triangle list called set normals independent flat. So if you have a mesh and its faces are flat, it doesn't have normals that are interpolated, then what you can do is you can call this function on it, and as long as those faces are all independent, it will calculate the normals from the geometry using the cross product, and then it will set those normals. And then in box.cpp, what we do is we modify the vertex to have a normal in there, and we call make independent for cube, and then we call set normals independent flat, and that will give us the normals for our cube for all the different faces. And obviously we're going to be changing the shaders here. We're adding light constants to our pixel shader. Obviously here we're deleting the constant buffer for the colors now. I'm going to have to add normal to our input layout. And that's about it. That's all the changes that we needed to make here. Now there's one other major set of changes that are in this commit. And well, if you look here, you see that we have this constant buffer, light constant buffer. But how are we setting this? Where do we set this light constant buffer? You didn't see it in the cube, and it doesn't make sense to put a light inside of a specific drawable. Lights are global to the entire scene usually. So where does it come in? Well, I've created a new class called point light. It doesn't inherit from bindable or anything like that. It encapsulates three related pieces of data into a single class with an interface. So what are the pieces of data? Well, you got the position of the light, obviously important. You have a mesh that is going to be the representation, the visual representation or indicator of the light in the world, which is very useful for checking our simulation. And then you have a constant buffer that is going to be the constant buffer that updates that light constant in our pixel shader. So those three things are wrapped up into here. Here's the definition of the light constant buffer. It has a float 3 for the position and an additional float for the padding so that it adds up to 16 bytes. And you've got functions here to bind and to draw the mesh here, the solid sphere mesh, to reset the position, to spawn a control window for controlling the light, and a constructor. And if you look at pointlight.cpp, the constructor is very simple here. Control window controls the position of the light, gives you a reset button that allows you to reset the position. Reset, very simple. Draw sets the position of the mesh and then draws the mesh. So the position here is set based on the position that is stored in our light object. And bind updates the data for that constant buffer, the position, with the position stored in this object. Now you can see here we're using something called a solid sphere, and that, if we look in here, that is a drawable. Here's some drawable base. And it's very simple. It's a sphere. And it is using a shader called the solid pixel shader, which has its own constant buffer. It just stores a single solid color, and that color is used to shade the pixels. The vertex shader for that is also, incredibly simple. Now, one change here that I kind of glossed over, but the constant buffer changed for the Phong vertex shader, splitting the transforms into a model-only transform and model view projection. So in order to do that, we also have to change our transform cbuff to store those two different types of transforms. So we define a structure for that constant buffer with two matrices in there. And then here, when we call bind, we initialize that structure with the model transform and the concatenation of the model, the camera, and the projection. Call update and bind as we were doing before. And finally, in app.cpp, we include the point light. We add a point light object to our application here. And finally, in app.h, we include point light. We add a point light to our application. And here, we initialize our point light. I've removed a bunch of these types here because we haven't implemented them yet. So now all we have is in our factory, all we have is the construction of a box. That's the only option so far. And in doFrame, every frame, we add an additional step of binding the light to our pipeline, and also drawing the indicator of the light after we've drawn all of our drawables. And down here, we spawn also the ImGUI control window for the light. And if we run that, we see that it sort of works, but not really. This isn't really what we would have been expecting, right? So, I mean, if we... let's turn the simulation speed down a bit here. All right. And now let's take a look. I mean, obviously the lighting is just too powerful. Anything that faces the light is immediately lit up to white, which is too much, right? What happens if we move the light around? You'll notice that I'm moving the light here left and right. It's not changing the direction of the light. So there's a problem. There's some problem here, perhaps multiple problems, but we're not really sure right now what they are. Now let's take this opportunity here and test out the graphics debugging facilities of Visual Studio. So we do start graphics debugging, and that is going to start our program like this. And we've got this report here. I don't know what it is, but it's capturing data about our program, some performance data, some other bull crappies. Now, what we got to do is we've got to take a snapshot of the processing of a single frame, and then we can use that to diagnose the shader. So, doesn't really matter which frame we take, but let's take this one. All right, so I've captured a single frame here. Once you've done that, you can safely close this. And now the view is going to change here a little bit. And what you can do is you can double click on one of your captured frames in here. And that is going to open up the debugging Pandora's box. I don't know what you want to call it. Doesn't matter. But it's a very big window. It's a big boy. I'll have to resize it a little bit. All right, here we go. So you've got a lot of stuff here. It can be quite daunting. But you should start off just by, exploring a few of the features, getting to know them, and then expanding up from there. Now, the one feature that I'm going to show you is how to debug the pixel shader and the vertex shader. So what you do is you can select a pixel in this frame here, and it will tell you the story of that pixel. So let's select, say, this pixel here. This one right here. I know this pixel because it's got two objects that were used that kind of overlap this pixel here. And we can see here we've got two objects with draw calls that have some bearing on this pixel. So one was drawn, and the one was drawn was the one in front. We know it's the one in front because the second one, it had the Z, here we go. It was excluded because it failed all the depth tests. So this was excluded by the Z buffer. So we can expand one of these draw calls, and it is going to show us a primitive here. Single primitive was affected in here, and that was a single triangle. And if we open that up, we get the vertex shader, we get the pixel shader, we get the results of the output merger. So this is what the render target was before. This is what our pixel shader was trying to render, and afterwards we got this. You can expand the vertex shader here, and you can look at the individual vertices and those attributes that were passed into the shader. But I suspect the problem is with the pixel shader. So let's debug it. You can do that by clicking on this start button. And now we are in our HLSL file for our shader. And there's a weird thing that I've noticed, and it might be the same for you or it might be different. But the locals, the autos, they're useless. They don't have any good information in here, or very little information. It's all weird. But it still works. What you do, well, let me show you. We're going to step over here where it's going to initialize some things. Now look at the V2L, not in scope. If you mouse over it, you get information about these variables still, even if they're not in this watch window. I don't know why the watch window, these locals, is borked for me. It makes me sad, but that's the way it is. But if I step over here, then I go to V2L, now we see, look, we've got our data in here. So it is working. We can inspect our variables as we step over our shader, and that's going to make our life a lot easier. It's going to make it easier to debug the logic of the shader rather than just staring it down. So what we do, vertex to the light, seems plausible to me. If we look here at our light, it's right around here. This one is probably behind the light. Well, it says Y is negative and X is negative. And if we look here, yeah, Y is negative and X is definitely negative. So, I mean, I'm inclined to believe the story that this is correct. And then the distance should also be correct. And it is, it's 11. And what else do we have here? Direction. Yeah, that looks right. It looks pretty much proportional to what we had here. Well, so yeah, these things, once they're not used anymore, they go out of scope. So we can see here that V to L and dis to L. Dis to L is still important, but V to L was only needed to calculate dis to L and dir to L. So after it wasn't needed anymore, it goes out of scope. So another little annoyance here. So now we calculate the attenuation. Now if we step over this, we see that our attenuation is 147. All right. Now we're going to, our diffuse value is the diffuse color times the diffuse intensity times the attenuation. Now our attenuation is supposed to make it smaller as we go further away. But now if we look at our logic here, we can see our attenuation is a very big number, 147. So when we step over this, our diffuse is going to be 29, 29, 29. Now remember, 1 is maximum. So we're 29 times the maximum color value in each of our channels. And that should probably tell us there's something wrong here. And obviously if our attenuation, well, it's out of scope now, but it was like, what, 147 or something? That's too high. And then we look at our logic here and we can see, oh, right, because attenuation is supposed to be 1 divided by, it's basically inverse square law, right? But we forgot to put the inverse in here, and that is why we're getting blown out, and that is why we get all that white. So we can close out of that debugging stuff. And we can close this window here and say, no, don't save it. And let's go into here, and let's fix this. 1.0f divided by, and we're going to divide by all this stuff here. Now, if we do that, we get something that still isn't great, right? We've gone a little too far in the opposite direction now. We're not getting any lighting. Although, if you look very closely, you can see we're getting a little bit of lighting on the faces that face our light. So it's working, it's just not working as much as you would expect. And to make a long story short, the reason why is because these coefficients for attenuation, I just put them as 111. I was going to change them later, but I forgot to change them. So 111 is too high attenuation for our scene. By the way, if you're interested in appropriate values for attenuation, you can check out this link here, and they've got some good information on different values of attenuation for different ranges. So these ones are a good rule of thumb to at least get you started. So if we look at this commit here, we can see that yes, indeed, I did the inverse here, and I changed my attenuation constants to be 1, 0.045 and 0.0075. So the quadratic one is way lower. And now if you run this, you're going to see something that looks a lot more like what you would expect. I can rotate around my scene here, and it does indeed look like it's being dynamically lit. However, there's still some problems, because look what happens when I move my light. We've still got that issue of the light position not affecting the rendering of the scene. No matter where we move our light in the scene, all of our other objects are being lit as if the light was at 0, 0. All right, let's see if we can try to debug this with the tools that we have at our disposal. So we'll start graphics debugging. We get our familiar screen now. And we can actually use the keyboard to print screen. And it makes a nice little sound. We take a little screenshot of our rendering. That one looks like a bunch of stuff is obscured, so I'm going to take another one. No, I don't want to take it with the light at 0, 0. I want to take it with the light at another position. So we'll put the light over to the left-hand side, and we'll wait for some big stuff to get out of the way. And let's take a screenshot now. Okay, so we got that screenshot. Seems like it'll be usable. We'll close this off. Then we're going to open up this screenshot, this frame, and let's see if we can analyze it. Wait, I opened up the wrong one, it appears, because this one is all obscured. So let's open up this one. That's better. All right. So first, let's take a look at the pixel shader, see what it can tell us. So we'll pick a pixel. It doesn't matter which one. Let's pick this one. It's nice and bright. And we're going to go into draw index to triangle. We'll run the pixel shader. And what we're going to see, let's see if we get our light position here. We do, and it is 0, 0, 0, which is kind of what we expected from what we were seeing, but it's not what we were going for because we moved the light to the left. So we know that the pixel shader is getting the light position at 0, 0, 0, even though that's not the one we were intending. So that's more information that we had before, a little bit of confirmation there. We can stop debugging. Now, another thing that we can do is we can look at the actual constant buffer data as it was bound. So if we look here, we can see that this was draw number 2958, or it was, command number 2958. And so we can scroll to 2958. 2958. There it is. And we can look down here at the pixel shader. We can see pixel shader constant buffers. And we can see where in our CPU code this pixel shader constant buffer was actually bound. And we'll notice something a little weird here if we think about it. The call used to bind the pixel shader constant buffer was from PS light constants. That's part of our box. And that is a little strange because the thing that should be binding this constant to our shader is not the box itself, but it is the global light object, right? Individual boxes don't manage the light. The light is outside of the boxes, but yet we're getting this thing here. So what we could do is we could actually go to this line in our code, if we can find it. Yeah, line 77. If I double click it, it might even open it. It does open it. And here we see, yeah, it's calling bind, but this isn't super useful because that's just from this class here, the constant buffer class, and it's always going to be this class that does the bind. The interesting thing, the thing that we really are wondering about, is that this class, the pixel PS light constants, that was created inside a box, inside a box's constructor. So let's look at box's constructor. So if we look at box's constructor here, we see a little bit of a problem. PS light constants bind, but there are no light constants, right? This light constant shouldn't be controlled from the box. It should be controlled from the light object. So this doesn't belong here anymore. So just a little bit of a brain fart. I had the old light constants, or I had the old pixel shader constants for the color index or the color lookup table, and I just turned that into light because I figured, oh, we're going to need light now. But really, that was going to be managed by a totally different object now. So with that out of the way, what happens when we run it again? We can see if I run the simulation, I pause it, and I move the light around in here, we're still not seeing any change dependent on light position. So there must be another problem. So again, you can see here I've captured a frame. I've got my light off to the side. Let's choose a pixel. We can see that that pixel corresponds to draw call 477. Let's take a look at 477. And if we expand it here, well, let me show you something interesting. If we select draw call 477, we can actually see the state of the frame buffer at the time that that draw call was executed, which is interesting. Let's look down in here and we can see again, we go to our constant buffer. It is now object 9. That's the constant buffer being used for this draw call. Interesting. So set by previous frame. So it wasn't even set in this frame. That's more information. If you look at object 9, that's down here in the object table, we can see, so the data for this one is 1, 1, 1, and what looks to be some kind of garbage value, because that number is way too big. And all these clues put together, they paint a pretty clear picture to me. So because this was set by previous frame, that means that our light position, the constant buffer, wasn't bound in the frame, and it's probably not being bound frame by frame. So it's only being bound on creation. That's a problem. So we want to, so it already gives us a place to look in our code. Look to the place where the light constant buffer should be being bound. Now the other thing we can notice about this is the actual data. This 111 doesn't seem random. So if our light constant buffer isn't being bound to that slot, well, what else is being bound? Well, we know that that slot is actually shared by the constant buffer that is used for drawing the indicator for the light, the solid color. And that solid color is white, 111. So we can see that our light position isn't being bound, and the solid color for the solid shader is just remaining in that slot from frame to frame. One last little thing I want to point out, for all these objects here, there's a little hour or a little clock icon. You can click that and you can get the history for the changes made to that object. Now, you'll see I don't have any history. That's because I'm running under, basically because I'm running under Windows 7. But I believe if you run this under Windows 10, you'll actually get a history for all these different objects that you can look at, and that might give you additional clues. Just something to keep in mind. And if we look at the content of the next commit, we see that I did indeed remove that pixel shader constant buffer bind from the box, and I did add that bind call to our point light bind. And if we run this, we now see our simulation looks like it's working properly, and if I move the light, it is now indeed being dynamically lit based on the position of the light object in the world. Beautiful. Working as intended. But that's going to about do it for part 1 of this tutorial. Stay tuned for part 2, where we improve the constant buffer organization and flexibility. We implement specular highlights. We add other drawables besides cubes. And we're going to see yet another way that the graphics debugger can make our lives easier and sexier. Until then, thanks for watching. Hope you enjoyed this video. If you did, please click the like button, helps a lot. And I will see you soon with some more Hardware 3D.